Okay, here we go. Kinesiology 230. This is chapter 4, presentation 6. I set this up very much like we've done before. There's a ton to unpack here, and we have different subtopics when we're talking about mechanical foundations. I broke it out into these four in a presentation, and then the remainder will be in the next presentation. So we look at four distinguishing characteristics of muscle. It has the ability to respond to stimuli, the contractility, the ability to create a pulling force, which we saw in the cross-bridge attachments. We already talked about the actin and the myosin working together. The extensibility, so it has the ability to lengthen or stretch, and we talked a little bit about that briefly when we talk about elongating muscle fiber and the cross-bridge attachments seen in eccentric loading. Then you have elasticity. It's the ability of muscle to return back to its original shape when force is removed. Now you have two components to that. One of it is when you're talking flexibility, you have elasticity and plasticity. Just for right now, just stick with elasticity. We'll focus on that. So with the muscle itself, you have these contractual components that, they're structural elements that help create force, right? It's the muscle fiber itself that we talked about in the sarcomere that actually makes the contraction happen. But you also have this non-contractile component in there that's also like the connective tissue that doesn't contract per se because there isn't a contractile component at all, but it's connective tissue that runs through the muscle fiber, and it's very much like the paramecium, epimecium, and the endomecium that we talked about earlier. And within the fibers themselves, they have different fiber arrangement. With like a 236, if we go into kinesiology 236, that's a little bit more specific where we talk about and differentiating between these different types of muscle and how they're set up. But you can see over here, radiate over here, longitudinal here, fusiform where it has like a belly, bipinnate where you have almost like a feather, right? Multipinnate where you have the feathers are going in different directions. And then you have unipinnate where they're all going in the same direction. So understand that you have fusiform, like this one down here, where all the fibers are running parallel to a line between the origin and the insertion, that's referred to as the line of pull. Then you have pinnate, where the muscle fiber runs at an angle to the line of pull. I don't really have to go too much further into that for this class, but as we get into other classes, we dig in deeper with that. So with the length and tension relationship, you have a combined effect, of all the muscles elements. That's everything we just talked about, where it's a contractile component and a non-contractile component. And force is produced by the muscular tendinous unit, right, which is kind of like the muscle and the tendon all kind of working together. And there's a limiting factor here in terms of the length of the muscle itself. And what they do here is they have this listed in terms of, all right, so in the chart above, which was right from our book, you have this functional range. And the functional range itself is very much this, it's inverted U that you have here is the active component of the range. So we have a range where you can take a muscle through, whether it's a movement pattern, but there's a functional component that's the active component right in the middle of this green line here. And it represents the contribution of the sarcomeres in producing force. And as we saw, when you do a contraction, the myosin pulls the actin, and the actin pulls because it's the I and the Z towards the midline. And what happens is you can only contract so far. The fibers don't overlap with one another. They can only go so far, and there's a limiting factor in there in how far they can go. And so there's a mechanical limitation that's built in. And with that, you have the length of the muscle, but you also have the length of the sarcomere itself, which does play its part. And I'm going to get this out of the way here. They elaborate a little bit further. They talk about the filament pressure against the Z lines and diminished capacity for myosin binding because it can't pull anymore. It can't take a little cross bridge across and pull the myosin. The myosin can't pull the actin like it's rowing. It just doesn't. It's limited at that point. So, you look at this chart and try to make sense of it. And it's really what they're after is where the active component is within the functional range. And it comes down to the sarcomeres as well as the length of the muscle. Let me get this out of the way. And that's what they really get into here in this section of the book. It's just that functional range that you see in the graphical interpretation that they try to present here. With force velocity, moving through our list of stuff here, force velocity, it's ability of a muscle to generate force, and it depends upon the speed of the contraction. When you have a faster contraction or a faster movement, in general, the greater the velocity of the movement, the lower the force that can be produced. So for example, like isometric contractions can hold way more force than any concentric contraction at speed. And additionally, when you get into velocity going from 0, which is isometric, to over here, which would be eccentric loading, where it's getting longer and longer and longer, muscle can yet again handle more weight. So we find that when we work out, we can do like 135 on bench press. We can push up 135, but we can actually handle 155 on the way down. And it's because we're mechanically stronger on the eccentric loading side, but you also have within the component of velocity, when we start talking about slower speeds, the slower the speed, the more weight we can handle. So you have two dynamics that happen here in terms of concentric and eccentric loading, but you also have a speed component that happens, and you can play around with your programming and do higher velocity, like on bench press, you can do speed reps, but you're going to have to do your speed reps at a lower weight. So if you normally bench 135 for sets of 10, you'll probably have to do your speed reps, like fast reps, at 95 pounds. You have to take weight off for that to work. I'm going to break out from there. I could talk about that for like 3 hours, but I'm going to stop there so I don't bury you guys in more details. But just realize when we talk about this curve here, as the speed increases, we have to lower the weight because the ability to generate force drops. It's an inverse relationship, right? Speed goes up, we have to drop the resistance. As speed goes down, meaning velocity goes down, we can increase the resistance because our muscles can handle more weight. All right, guys, signing off, moving on to the next one.